My name is Lyndon Saunders. I'm one of the directors at FAR, and this is Joe. He's one of our engineers focused particularly on battery lightweighting. We design, for those who don't know us, we design, develop and produce composites, and we come from a strong automotive background. We think car companies need composites that are cost effective as well as light, and that's a big focus for us. And we think that means that sometimes you need to be pretty clever about how you design something. And you always need to be careful about putting the right material in the right place. That's for us is a key in a design process, and I think that sometimes means we need to design differently, and we're very calm and happy with that. We're here today to talk to you about a specific example of using different materials in the same structure in order to achieve the lightest and most cost-effective solution for a customer. And with that brief introduction, I shall hand you over to Joe.
Hi everyone. Thanks for joining today and listening to what we have to say. I'm going to be talking today about using multiple materials together for better electric vehicle battery enclosures. As we all know, the electric vehicle market has been expanding rapidly over the last few years and is set to expand even further moving forward. It's estimated that 25 to 30% of lightweight vehicles will be electric or hybrid electric by 2024. And the UK will be producing 1.6 million electric vehicles by 2040. So because of this, there's a huge market opportunity for disruptive technologies to become established in this market. When it comes to consumers, they're most interested in the range and cost of their vehicle. Reduction in the vehicle mass has a correlation with increased range, but also has other benefits such as reduced CO2 emissions, but also other advantages such as reduced energy and crash. You're reducing the total mass of your vehicle. You can reduce the burden away from your heavy crash structures which currently exist and further lightweight your vehicle. So a typical battery tray is a 70-odd kilogram enclosure which features cast, extruded and sheet aluminium that houses the battery pack. So we're looking to reduce the weight of these structures. Currently, an electric vehicle consists of battery cells, which is surrounded by the battery enclosure, and these cells are controlled by externally packaged power electronics, known as the battery management system, or BMS. These power electronics require thermal management, so each of these separately packaged components require its own cooling system, which is additional weight on top of the structural weight, as we now have multiple systems doing the same thing. Around 11 kilograms of copper wiring required to connect these separate systems together. So we want to be able to design a structure which allows for the distribution of these different systems closer to the systems for which they're controlled. And we want to be able to package them efficiently where we're reducing the number of separate components. So for example, using the same cooling systems as cooling loops for multiple electrical systems. And we're also looking to reduce weight by moving away from unnecessary heavy metallic structures towards lightweight composites. So battery cells and power electronics both require thermal management, which usually comes in a form of heavy heat sinks, which are usually aluminium. The bar chart in the bottom right shows a heat transfer of the two different structures. One of the structures is wholly aluminium 5754, and the other is a carbon fiber composite with 25 by 25 millimeter aluminium block embedded through the thickness. Carbon fiber is a relatively poor conductor of heat compared to aluminium. Aluminium is around 200 watts per meter Kelvin, whereas carbon is around 0.5 watts per meter Kelvin. The blue on the bar chart is the heat flow through the structure, and the yellow is the temperature of the heat source. And this heat source is analogous to the temperature generated from a battery cell or a power electronic circuit. So the way this experiment worked is we had a 40-watt heat source, which was applied over a 25 by 25 millimeter area on one side of the coupon, and a water cooling block is in contact on the other side of the surface. So our heat is flowing from our heat block through our structure and into our water cooling block. And by measuring the change in temperature in and out of that water block, we calculate the heat flow through the coupon. And we can see that there's virtually no difference between the performance of these two coupons. So by replacing the aluminium with the carbon fiber, apart from that that's in contact with the heat source, we've just achieved a 30% weight reduction between these two coupons. So we've showed that only the contact point is important to be highly thermally conductive, which allows material choice in the surrounding structure. For this case study, we've ignored galvanic corrosion, but in reality, you could use carbon and copper or glass and aluminium, and you'd get the same results. So now that we know we only require thermally conductive material to be in contact with a heat source, we can look to optimize that further. The pictures of the coupons on the right-hand side of the screen show different amounts of embedded aluminium. So starting from the top, it's 100%, 50%, 25%, and 12.5% of the heat source area. The heat transferred, we perform the same experiment and plot the results. And as we expect, the heat source for the structure is linear to the amount of aluminium in contact with the heat source. And then this results, which is the blue line, and then this results in a lower heat source temperature, which is the yellow line. So we can reduce weight further by optimizing for our application. So, for example, if the application requires lower operational temperature, more aluminium can be used. If there's an application which has a higher acceptable operational threshold, we can use less aluminium, which would result in a lower weight structure. So we also found that the cross-sectional area of the thermal conductive material isn't the only factor influencing this. The geometry of your high thermally conductive material is also important. So the picture of the coupon shows 12 4mm diameter rods, which the total area of them is equivalent to 25% of the heat area. By spreading the same amount of aluminium out over the heat area, we can achieve greater results without increasing our weight. You can see on the graph the two bold data points. We have a lower heat source temperature and a greater heat flow. So we can optimize the geometry of our thermally conductive material to achieve better results. And we can do this with existing packages in finite element analysis software, such as topological optimization, where we'd be optimizing for the heat flow versus the weight, and we can add all sorts of parameters to make that manufacturable in that process. So bringing it all together, we manufactured a simple battery box concept to highlight some of these points. So we have a carbon fiber composite shell, which houses both the electronics and the battery cells in a modular design. And we want it to be modular because if individual cells and circuits are damaged, they can then be replaced without replacing the whole battery pack. The power electronics are on the surface of the battery box. These are, in this case, voltage balancing circuits. When a battery cell is charging, when a battery cell is charging, it modulates the charging flow between them based on how much the individual cells are charged. Under the area where the temperature is generated from these circuits, we have embedded aluminium, which acts as thermal paths, taking heat away from the electronics into the cooling pipe. And the same cooling pipe is in contact with the top surface of some battery cells. So we've reduced our number of components, and what would conventionally be two separately packaged systems, we've combined into one. So we've reduced weight by optimizing the amount of aluminium, and we've also reduced weight by reducing our piece part count of our vehicle. And this has a knock-on effect on reducing the cost of consuming. Oh, no, one more. There we go. So this case study found that we can combine multiple materials together using heavy materials only where they're required. High thermally conductive materials only need to be in contact with a heat source, which allows freedom of material choice in the surrounding structure. At FAR, we are active in other sectors like aerospace and light rail, apart from automotive. And we hear the need for lightweighting of structures from all of these different sectors. Other drivers are miniaturization of power electronics. And when you miniaturize electronic circuits, they require more efficient cooling solutions. And we think this way of thinking and designing structures addresses all of these issues. So by using multiple material types together, the architecture of electric vehicles can be reimagined. We can integrate multiple systems into the same structure, which reduces our piece part count and hence our weight and costs. I'm going to hand you back over to Lyndon for some closing remarks.
Thank you, Joe. So I think we've seen from Joe's talk and the work that he's done on this that we've shown that using a multi-material approach in this space really does work. That actually opening our minds to be able to choose as widely from that palette of alternative materials as possible really does help. We've shown we understand what combinations of materials that we'd use in these applications for what I'm going to call generation 2 battery boxes. So moving away from the traditional big heavy box and trying to come up with a more efficient solution, particularly going back to Joe's point about galvanic corrosion and the selection of materials that go together is critical. And we've shown we've got a grasp around that. We've also shown we've got a good starting point for the design of a new kind of battery box and the direction to follow with it. So we feel we've ticked all of those boxes. What we're now looking for really is a vehicle maker who's got the design, who can give us the design freedom to put all of this stuff actually into practice on a vehicle. That might be as a customer, it might be as part of a research consortium. We're pretty flexible at that kind of stuff. We just want to see this technology out moving around. We're quite calm about the vehicle too. So we've done structural work for composites for things as small as a motorbike up to, as Joe alluded to, as big as a battery electric tram. And we're also doing some aerospace work. So we're pretty laid back about exactly what kind of battery electric vehicle, but we'd love to get this onto a battery electric vehicle. And with that, we'll move on to questions.
Perfect timing, as usual, as per the last presenter. You guys are really good. So excellent, really good presentation, and really timely. I think everyone will recognise that you know, that the battery box with the electrical connections is going to be becoming key. There's a couple of questions in the chat. So the first one from Shanta Desai: have you tested it for thermal runaway and pressure buildup?
So this seems to be a common theme in the questions. For this application, no, we haven't. This was just a concept to highlight some of the points of our research. We are currently developing projects in which we are developing integrated cooling solutions for battery boxes, and these will undergo thermal runaway tests. Wonderful.
And further question from James Grant: what joining methods have you explored for the mixed materials, and with what success?
So these are bonded in with thermal conductive adhesives. It's actually quite a good topic for us at FAR. We've got a lot of experience with multi-material structures, especially designing crash structures, which are made out of multi-materials. And we have a lot of experience working with suppliers of adhesives to facilitate that. So it's kind of a hot topic for us here.
Excellent. And a question from Will Searle: with your cross-sector work, do you see demand for integrated batteries within structures, or is the demand for boxes that are unintegrated?
I think what I might refer to as generation 1 boxes are very traditional, big, heavy, bulletproof, practically boxes that everyone leapt to when batteries and battery controllers and power electronics were all segregated. I think as people start to see the weight of those, I mean, I've seen one, for example, 200 kilos of battery required 100 kilos of box to protect it. As OEMs start to see just how much those boxes are weighing, we're seeing increasing demand for something that's just a little bit cleverer than a big heavy box. So we're seeing that kind of interest from all over the place. You know, aerospace companies, as they start to look at electric aircraft, car makers, truck makers, tram makers, all sorts of people are starting to look at the tradition, let's say the traditional generation 1 box, and realizing that it's just too heavy.
And if I could add something quickly onto that, I think there is a requirement for all sectors to simplify piece part count, and integrating multiple systems together does that, which reduces knock-on costs to consumer, but also simplifies the architecture of the vehicle, which for ongoing running costs for the consumer simplifies maintenance and yeah.